In this video, we look at optimization with multiple variables. Some of this can be found in Dixit Chapter 8. So we start with what we'll call a utility function, which is a function of x and y. And we find that, first off, the necessary conditions for an extrema, or a maxima, or minima, are that the first derivatives, the derivative of the utility function with respect to x and the derivative with respect to y, are equal to 0. However, knowing this may not help you identify whether the point is a maximum or a minimum, or perhaps what we call a saddle point. So therefore, we need to have sufficient conditions. In the case of one variable, we found that the partial, or the derivative rather, the second derivative of y with respect to x squared was less than 0, which implied that the curvature was convex upward, as when we have a maximum for the one variable case. For two variables, we find something similar to the one variable case, but we must also consider the cross, what I'll refer to as the cross product term. A sufficient condition for a maximum, then, is that the second partial derivative of the utility function with respect to x is less than 0, and that the second derivative of u with respect to y is also less than 0. But more importantly, we have to consider this term here, and that term, and I forgot square here, or a superscript 2, that the second derivative of the utility function with respect to x and the second derivative of the utility function with respect to y, when those two are multiplied together, they have to exceed the cross partial. So the second partial derivative of the utility function with respect to x and with respect to y squared, all right, the first two partial derivatives, second order partial derivatives, have to exceed the cross partial derivatives raised to the power 2. That's for a maximum. For a minimum, we get the same first order conditions, that the first derivatives of the function have to equal 0, and that the second derivatives now have to be greater than 0. All right, so the partial of the utility function with respect to x, the second derivative that is, has to be greater than 0, and the same thing is true for y. And we have the same condition for a minimum as we had for a maximum. In other words, that this second derivative with respect to x multiplied by the second derivative with respect to y has to exceed the second partial derivative of the utility function with respect to x and y, but then squared. Note that if the second partials of x multiplied by the second partials of y are less than this cross product term squared, we end up with a saddle point. If they're equal, in this case, where the second partials of x multiplied by the second partials of y are equal to d squared u partial squared u divided by the partial of x partial y squared, then we have no information to tell us whether we're at a maximum, a minimum, or at a saddle point. Consider the following example. Utility is given by x cubed plus x squared minus xy plus y squared plus 4. The first order condition gives us 3x squared plus 2x minus y equals 0, and that the partial of u with respect to y is minus x plus 2y equals 0, which gives us that x is equal to 2y. So we use this information, x equals 2y, and we put that into the first derivative with respect to x, and we get 3 times 2y squared plus 2 times 2y minus y, equal to 0, and we can solve for that, and we get 12y squared plus 3y equals 0, which when we bring the 3y to the other side, or rather we could do, we get rid of one of the y's, we get 12y plus 3, which gives us minus 3 over 12. So we get minus 1/4. So that is one of the two solutions that we can get. The other solution, of course, is that y equals 0. If y equals 0, then it turns out that x is equal to 0 because x is 2 times y. If y is minus 1/4, then we get 2 times minus 1/4, we get minus 1/2. So we have two solutions, and we need to look at the second order conditions for each of those. So we take the second partial of the utility function with respect to x, and we get 6x plus 2y. If we do the same with respect to y, second partial of the utility function with respect to y, we get 2. And we get this cross product term, if you like, the second partial with respect to x and y is equal to minus 1. Where do we get that? Well, we just take this, and we get with respect to x, we get minus 1. If we look at this one, and we take the second partial with respect to x, we get 6x plus 2. And if we do it with respect to this one, we get 2. So the second order conditions for this are given by these general formulas, and for y equals 0 and x equals 0, we find that this second partial with respect to x is 2, which is greater than 0. We do the same thing with respect to y. It also is equal to 2, and it's also greater than 0. Then if we multiply u xx, where the two x's, the subscripts x, indicate this exact thing here, and we multiply that result, 2 times this result, which is d squared u partial y squared, which is 2. So we multiply 2 by 2, and we get 4. All right. So then the question is, what is the value of uxy squared, which is simply that second partial derivative of u with respect to x and y squared? We get minus 1 squared is 1, and we find that 4 is greater than 1. So this holds here, which, if we go back, is a requirement for both maximum and minimum. So we know that we have the conditions for a minimum satisfied. All right, the minimum, because the requirements for a minimum are that these partials have to be greater than 0 in both cases, and that's exactly what they are. All right, 2 is greater than 0, and 2 is greater than 0 there. Now, for the other point, minus 1/2 and minus 1/4, we get uxx is 6 times minus 1/2 plus 2 equals minus 1. Uyy equals 2. These cross terms, again, are minus 1. And we find that uxx times uyy is less than uxy squared. Minus 1 times 2 is minus 2, which is less than minus 1. So we find that there's a saddle point at minus 1/2 minus 1/4 because this holds. All right, that second order condition holds. So we can summarize these results in this little table, that table there, which for a minimum, the first derivatives have to be 0. For maximum, the first derivatives need to be 0 fxx, so the second partial derivatives of x have to be less than 0. The same is true of the fyy, and this has to be the case that fxx fyy minus fxy squared has to be greater than 0. For a minimum, we find the same thing, that they have to be equal to 0, the first derivatives. The second derivatives have to be positive instead of negative. For a maximum, they're negative. For a minimum, they're positive. And again, this equation here, fxx fyy minus fxy squared has to be greater than 0. Now we can also look at the saddle point. Saddle point requires the same first order conditions, same conditions here, and that has to be less than 0. This fxx fyy minus fxy squared has to be less than 0. If it's equal to 0, there's no information, and we cannot tell whether or not we have a maximum or a minimum. And we can show that a little bit in a diagram later on. But basically, I may have even shown it in a previous diagram where what you get is something like this. Okay, you get a function that comes up like this and like that, and then this point here is the point where you have no information. Okay, let's look at the necessary and sufficient conditions when you're using differentials. So again, we have this same function where utility is a function of x and y. We take the total derivative of it, du equals fx dx plus fy dy, where fx and fy are in the interpretation of utility, your marginal utility with respect to x, your marginal utility with respect to y. But if this is a production function, so in other words, this is somehow output, then it would be marginal product of x and marginal product of y. Since du has to equal 0, all right, that has to equal 0, then, and dx and dy can be any value, then the condition required for the above equation to hold is for f of x equals 0. All right, if this is 0 and this is 0, then that condition will hold. Now we can look at this as a three-dimensional bowl. The surface of the bowl represents the utility or output. As we move down the slope of the bowl in this direction here, all right, utility or U is decreasing at a decreasing rate. So utility or output is decreasing at a decreasing rate, and here it's increasing at an increasing rate. So utility is decreasing at a decreasing rate, it hits the bottom, and then it increases at an increasing rate as it moves up the right-hand side of the bowl there. Thus, a sufficient condition for a minimum is that this d squared u has to be greater than 0. So the second derivative of u, the second differential of u has to be greater than 0. So here again we have conditions for a maximum and a minimum. So the first derivative, total derivative, has to be equal to 0 for a maximum, and that d squared u has to be less than 0 for a maximum. For a minimum, again, du has to be 0 and d squared u has to be positive, where d squared u is simply the second partial derivative of x multiplied by dx squared plus the second partial with respect to y of d multiplied by dy squared plus 2 times this cross product partial times dx dy. So consider the following example: x cubed, u equals x cubed plus y cubed minus 3x minus 27y plus 24. The total derivative is f of x dx plus f of y dy, which is 3x squared minus 3, 3x squared minus 3, plus 3y squared minus 27 dy equals 0. So as I noted up above, the condition here is that f of x and f of y have to be equal to 0. So we get we get that this has to equal 0 and that has to equal 0. So 3x squared minus 3 equals 0 implies it's x squared minus 1. So x is equal to plus or minus 1. 3y squared minus 27 has to equal 0, so y squared minus 9 is 0, which means y is either plus or minus 3. And the reason is that du has to be 0 implies fx has to 0 and fy has to equal 0. So the second order conditions we find according to this formula that we mentioned above. All right, we've mentioned it up here. So we need to figure that out. So the first thing we do is we calculate what that is. So d squared u is 9x dx squared plus 9y dy squared. Then we need to check all points that are identified by the first order conditions. So let's look at x equal to 1 and then y equal 3 and y equal minus 3. So we look at 9 dx squared plus 27 dy squared, and it turns out it to be greater than 0. All right, because this is a positive term and that's a positive term because of the squared. So we have a minimum at that point because it's greater than 0. Then we look at 1 minus 3 and we get 9 dx squared minus 27 dy squared. And we don't know whether or not it's greater than or equal to 0. It's going to depend on where we are. So it's a big question mark. So we cannot say that it's either a maximum or a minimum or even a saddle point. So now let's look at x equals minus 1 and y equals 3 and then minus 3. And we find that minus 9 dx squared plus 27 dy squared. We don't know whether that's greater than or less than 0. So again, we get a question mark and we can't answer whether this is a minimum or maximum or what it is. But then for minus 1, minus 3, we get du squared equals minus 9 dx squared minus 27 dy squared, which is clearly negative, which implies that we had a maximum at this particular point. Okay, and remember, we're looking at what the value of u is at these points and not the value of the points themselves. We can also use matrices and determinants to find first and second order conditions. So we let utility be a function of x1 to xn. We take the total derivative, so we get f1 dx1 plus f2 dx2 plus ... fn dxn equals 0, and this is satisfied if all of the marginals are equal to 0. So f1, f2, which are the partials of f with respect to x1 and with respect to x2, those have to equal 0, and the same is true for the partial of f with respect to n. It has to equal 0. So the second order conditions require that d squared u is less than 0 or d squared u is greater than 0. If it's greater than 0, then we have a minimum. If it's less than 0, we have a maximum. So d squared u is simply this squared. So in matrix notation, we find that so we can convert this into a matrix notation, which we do here. So we get dx1 ... dxn. This is our matrix here, which is f11, f12. So these are your second partials with respect to, so f11, for example, is d squared u or d squared f with respect to the partials dx and dy. And the same thing, f11 is the partial of f, the squared second partial of f with respect to x1 and x2, and so on throughout this entire matrix. And then we have a vector, a column vector, dx1, dx2, etc. This particular kind of notation is referred to as a quadratic form. So for our above example, the example we had up here, okay, this one Where is it here? This one. For this example, we find that we get this expression, which is, okay, remember we're dealing now with basically two x1 and an x2. Then we have this expression here. The associated matrix is real and symmetric. So in other words, F12 is equal to F21. And this is referred to, this matrix here, which we've repeated here, is referred to as the Hessian matrix. So d squared u less than 0 implies that the Hessian is negative definite, which it has to be for a maximum. D squared u greater than 0 implies that the Hessian is positive definite for a minimum. So we can define negative definite and positive definite. A matrix is negative definite if the principal minors of the matrix, and remember now your matrix algebra, alternate in sign with the odd numbered minors negative. So in other words, F11 less than 0, F1, the determinant of F11, F12, F21, F22, the determinant of that has to be greater than 0, and they keep alternating in sign, and we can use that -1 to the power n to denote the alternating sign, because if n is 2 in this case, then it would be a positive, and so on. So we have F11 ... F1n, so this is the final. The determinant of the total Hessian matrix also has to be greater than 0 for a maximum. Well, that assumes that n is an even number. All right, a matrix is positive definite if the principal minors are all positive. So everything is positive. F11 is greater than 0. The next principal minor is greater than 0, and all of them, right up to the end, the determinants are all greater than 0, and then we have a minimum. So finally, let's consider this example. U is 2x squared plus y squared minus 4x plus 8y. First order condition, f of x is 4x minus 4 equals 0, so x is 1. Fy is 2y plus 8 equals 0, y is minus 4. Okay, that's pretty obvious because we have 2y minus, 2y plus 8 equals 0, 2y plus 8 equals 0, and then that's solved when y is minus 4. So the second order condition is that fxx is equal to 4, which is greater than 0. Then we look at the determinant of this particular matrix, which is 4, 0, 0, 2. Notice that symmetry there. And that's equal to 8, which is greater than 0. So therefore, we have the two that are greater than 0. This implies that d squared u is greater than 0, and we have a minimum. So we then calculate what the value of u is. Now let me just check that. Equals 2 times 1 squared plus minus 4 times squared minus 4 times 1 plus 8 times minus 4, which is equal to 2 plus 16 minus 4 plus, minus 32 is equal to 10 is minus 22, not that. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.